No, Latoya dropped the class. Lauren, though. Okay, here's a question that was on your last assignment. I just want to remind you of this question here. You've already had it marked. It was involving taking a function of f of x equals x squared minus 5x plus 6, and a second function, g of x, x plus 3. And I'd really like to focus on parts B and C. So, I mean, if you have that assignment, you can look at it again. I'm just going to quickly graph these guys. If you were asked to do the f gx, that means take this g of x function and shove it inside of both of those x's right there.
Parker Smith, can you please come to the office? Parker, please come to the office.
Does that make sense? Hopefully, when you graphed it, you got, well, let's change the zoom here. It's a bad idea. Zoom standard. Hopefully, when you graphed it, you got, here's a nice parabola, and right next to it is another nice parabola. And one of the questions I asked you guys was, explain how they're related. And for the most part, so long as you mentioned that like they're almost the exact same as each other, except one is like slid over a little bit, that's kind of what I wanted you to get. Does that make sense? That was that question. Today, I want to use this concept right here, but I want to give you like the proper math terminology for it. Do you guys understand, or do you know the term congruent? You've heard that before? We often talk about congruent with things like, say, triangles. That's probably where you might have heard it before. If you have a triangle, let me just draw one out here. Right here, that was like, this side was 3, this side was 4, and this side was 5. It is congruent to a triangle drawn like this. Pretend they're the same size. Obviously, I can't draw. Where this side right here is 5, this side right here is 4, and this side right here is 3. They are the same triangle. But are they drawn in the exact same like orientation? No. But are they the same for all intents and purposes? Yes. Okay. And the point of today's lesson is that we're often going to have a graph that is supposed to represent something. It could be a shape. Like say last year with parabolas, I would often use parabolas to be, let's see, what did we do last year? Like a ski hill. That was an upside down parabola. Does that make sense? Or I had one where there was supposed to be like a couple of posts, and there was like a chain link in between them, and that was a parabola. But maybe your parabola is in the wrong spot. Does that make sense? And what you might need to do is slide it over. That's the goal of today's lesson. Today's lesson is all about how can we translate a graph so that it's congruent. It still looks the exact same, but it's in a different location. Because we don't want it there, we want it here. That make sense? So I want to start out with just a basic exercise here. We're going to quickly sketch two graphs and compare how they're similar and different. So I don't need to like do this in great detail. Just to sketch this one, maybe we'll just do a grid like this. And we'll just go right to our graphing calculators. So let's sketch the graph of x to the third. So here's x to the third. So hopefully you guys kind of know this graph. It kind of does that little flippy twist right at the origin, and then keeps going. That's x to the third. So far, so good? Okay. Well, hopefully my kind of preamble is going to make sense here. What we're going to do is this graph right here, it is going to be congruent to the other graph. It's going to be exactly the same, only it's going to be shifted around. And I want to try to explore as to how it gets shifted around. So this graph right here is going to involve a bracket, an x minus 1, still cubing it, still being cubed. Where's the 3 button? And then after we're done, we're adding 3. It may be easier to actually take the other graph off, maybe, to see. I'm not going to do that. I'll just take this one off. You guys see how it kind of has that same sort of shape? But what's happened is the little flippy section is actually happening up in this region right here. It's doing more of this. Does that make sense? If we had the black graph and asked you to turn it into the red graph, what would you need to do to make one graph kind of translate into the other one? Can anyone find you put that into words? Okay, let me help out a little bit. Let's talk about the term horizontal and vertical. let's work with vertical first. What does vertical mean? Up or down? To go from black to red, do you have to go up or down? From black to red, you need to move the graph up. Does that make sense? The red graph is a little bit up from the black graph. Does that make sense? Okay, and then horizontal is side to side, so that would be like left and right. So is the red graph to the left or to the right of the black graph? The red graph is to the right. Does that make sense? So what we might say here in terms of terminology is that red is congruent and it is up and right. Does that make sense? Like that would be a terminology we might be able to use. The one graph, it's actually the exact same, believe it or not, as the other graph is. It's just been slid up and over. Okay. My goal here today is to show you how to do that based on the equations. And that has to do with this little number right here and this number right here. Because those are the two values that are what makes the two graphs different from each other. Anyone want to hazard a guess as to what the +3 accomplished? Not the intercept, but the +3 right here is actually what caused this graph to go up.
If it was negative.
Let's try it real quick here. I'm going to take this guy right here and move it down 3. Does that make sense? Driana, you made a point there about the intercept. The problem with this guy not being the intercept is that this is not in standard form. If we actually FOILed this cubic thing out, we'd get an extra, an extra constant term that we'd have to add to this +3. So this guy right here is not actually the constant term unless it's in standard form. Does that make sense? Okay, what about this -1 right here? I want to hazard a guess as to what the -1 did if the +3 moved it up, or as I just showed you, it moved it down. So let me just go back to where it should have been. Sorry, go ahead. What did you guys think it did then? Yeah, the -1 is what moved it to the right. Okay. Anyone want to hazard a guess as to what would happen if this had been a +1? Yeah, let me prove that to you. If I were to have made this a +1 right here, we still have a congruent graph, but now it's been slid the other way instead.
Why is that? Like, why?
Can you, if I don't answer that question over the next 20 minutes, re-ask it again, because that's the whole point of today's lesson. Is that okay? So I've got some notes on this, like some technical notes here. Let me walk through those, and then maybe in doing this, hopefully I'll answer your question as to why. Okay. So if you want to take a graph and move it up or down, you need to do what's called a vertical translation. And basically what that means is after the function is over, you need to add or subtract a value. I'm going to put a word here. This is like after the function is done. So see how there's that +3 like way afterwards? What that's done is it's moved the whole graph up 3. Maybe I have a good analogy for this. Imagine that, remember how I talked about functions being a vending machine? So imagine that you put your money into the vending machine and it gives you back, I don't know, whatever it gives you back, right? Well, if you put a number after that, what that means is after you're done getting back whatever you get back out of the vending machine, after that you get 3 more. Right? And if every single time you get 3 more, what will that do to your graph? Well, it'll make everything go a little bit higher. Does that make sense? So by putting like a number well after whatever your function was, it makes the graph go up. If it happens to be a subtract sign, a negative, it makes it go down. Does that help explain why? So I've got another example in the next slide I'll do here. Let's just talk about how these graphs here work. Are these two graphs essentially the same as each other? I would say, yeah, they're almost the exact same. What's the only difference? Well, this guy's got a +3. So let's talk through what this function means. If you input the number 1, this means square that number. So if I gave you 1, you'd say, well, the answer is 1. If I gave you 2, you'd say the answer would be 4. If I gave you 3, you'd say 9. Does that make sense? Well, this is the exact same function. 1 would give 1, 2 would give 4, 3 would give 9. except on the end, it's almost like the machine malfunctions and gives $3 extra every single time. Does that make sense? Regardless of what you put in. If you put in $1, you'd still get $3 bonus dollars. If you put in $100, you'd still get $3 bonus dollars. Does that make sense? And what basically happens is it squares like it's supposed to, but afterwards everything gets 3 more. So if we were to graph these guys, here's your x squared, and here's your x squared plus 3. Hopefully you'd see here's the one quadratic, and there is the next quadratic right above it, and they are the exact same as each other. I know it doesn't quite look like it because like this guy right here needs to kind of go a little bit further, if that makes sense. But those are the same quadratic, only one of them is 3 higher. Take a look at the table of values. 4 gives 7, 1 gives 4, 0 gives 3, 1 gives 4, 4 gives 7, 16 gives 19. They're always different by 3. Does that make sense? Let me say that one more time. The function machine says if I give you $1, it squares it. But then the second one basically means, well, after, keyword here, after we're done, you get 3 bonus dollars. What that does is it moves graphs up and down. Does that make sense? What else should I talk about here? The concept of outside is the same thing as after. Okay. It only affects y coordinates. What it does is it moves the whole graph up down. So it doesn't actually change x coordinates, but it changes y coordinates. Here's a couple of other notations I'd like you guys just to be aware of, because it could come up. They could write it as y minus k equals f of x. Okay, here's how that works. It used to be f of x, like you had a function and you added k. Well, what happens if you bring this plus k on the right-hand side and subtract it to the other side? Does that make sense? So that's all that's been happened here is if this is one way of writing a function, your new function is equal to your old function, but adding a number, well, then what you could do is just subtract k from both sides. And that's what this notation here means. This last notation here means what you're really doing is you used to have a function, and your new function, whatever your x value was, is still the same x value. But whatever your y value is now a little bit bigger. So far, so good? Okay. So let's just talk through these things. What if I give you a new function, y, is equal to whatever your old one was, but now you're minusing 6? What's going to happen to your graph? It'll go down by 6. It'll be 6 lower than it used to be. I don't care what the function was. The function could have been cubic, quadratic, but whatever it was, when we're done, we're just making it go down by 6. Everything down by 6. So what does this one mean then? Perfect. It's going up by 3. What about this one then? What if I phrase it in this odd notation? What did you say? Yeah, this one is going up by 4. Yeah, the reason why is that it's just kind of messed around the notation, but this minus 4 really belongs on this side over here as a plus 4. So this one is up 4. It's just kind of a weird way of trying to mess with you, I guess. Yeah, this plus 2 really should be on the other side, so this would be down 2. Sound good? Okay, let's talk about horizontal translations then. Horizontal translations do not happen after a function occurs. These happen before. I can't spell apparently. That's supposed to be before. Undo. Be. Oh my goodness, I did it twice. Before. Or sometimes we use the word inside the function. Okay. Let me hop to an example maybe first here. Let's graph these guys. I don't know why I have stuff on here. Saved from last year. Do you guys see how here's the x squared graph? And here there is a minus 3 inside the brackets. It's not afterwards. For example, what we just did would have been x squared. and then x squared with like a -3 way over here. That's not what we're talking about here. Here we're talking about squaring. Before we square it, subtract 3. That makes sense?
So that changes the x.
That changes your x. Yeah. What ends up happening is rather than it going up and down, this is going to cause your graph to go side to side. Let's just show you.
So is there a name for this notation?
We call them translations. We call them either horizontal or vertical translations. I think that's probably what we'd call them. So here's x squared. And then here before, hence the brackets, before we actually do the squaring, we're going to subtract 3. You see how these guys are the same as each other? Okay. This one, I wrote on the slide back here, it may seem opposite to some people. Because what did a -3 do to the graph? It actually made it move that way. It made it go more positive. I have an explanation for this, but this is one of the hardest things to understand. If you can just accept that a negative makes it become more positive, that's all you need to know. But hopefully this will help make sense. Here's my analogy. You're going to put some money in the vending machine and it's going to square your money. That's what it does. But before you actually get to put the money in the vending machine, a bully comes and steals 3 of your dollars. Does that make sense? So you wanted to go spend your money. Apparently this vending machine squares your money. Before you were able to, though, someone stole your money. However, you're smart. You knew that the bully was going to steal your money because it didn't matter how much money you had. If you had $1 million, he was going to take $3. If you had $4, he was going to take $3. Does that make sense? So you knew in advance that the bully was going to try to steal your money. So what you did is you brought $3 extra more than you needed, so that you knew that when you got your money stolen, you still would end up with the money you were hoping to achieve. Does that make sense? Let me give you an example here. Let's say you wanted to eventually get $9. What number would square to get 9? 3. So should you bring $3 if a bully is going to beat you up first? No, because if you brought $3, he would steal your $3, you'd have none. And then when you squared your money, you'd still have none, and therefore you would get to none. Does that make sense? If you brought $4 would have squared to 16, but the problem was the bully stole your money, right? So the bully steals your $3, so 4 is now down to 1. When you square it, you have $1. Makes sense? So if you want to achieve 9, how much should you have brought? Therefore, why are the x values bigger? Because they had to be. Because the x values had to be bigger in the positive direction because it knew that it was going to get some money stolen from it.
So what about when that value is?
Okay, sure, let's do that one next then. So if a negative makes the graph go this way, and I'm pointing to the right, if I were to have made it an x plus 3, it's almost like the opposite. It's like rather than you getting money stolen, it's like you knew that you were going to find $3 laying on the ground. Does that make sense? And it doesn't matter how much money you were planning on bringing to this machine. If you were bringing $1 or $10 or $100, there's $3 that you just can count on finding there, right? Well, that means that you needed to bring $3 less because you could count on finding that $3. So what ends up happening is the graph ends up going more in the negative direction, meaning that the x value required is actually less than it normally would have been. So I write on this slide here, it may seem opposite, perhaps. It depends on how your brain works, I guess, in terms of interpreting it. Here's what you need to know. If it is a negative sign, it'll cause the graph to go that way and become more positive. And if it's a positive sign, it'll actually cause the graph to go this way and become more negative. Let me check here. If x is positive, the graph goes right. Yeah, that's wrong. No, wait. I've written this thing with a negative right here. So then it's kind of like if h is a positive number here, like if it's negative with a plus 3, then it does go right. But if it was like, if it's x minus 3, then it actually makes it a positive and it goes left. That might be a little bit confusing. Maybe we should change that then. Maybe you should just say, like, ignore this already there negative sign. If all of this thing right here, if that is a positive numbers go that way. And if all of that thing right there is a negative number, it goes that way. as long as you can remember what happens, you're good. If you can interpret why it's doing that, that's even better. So let's do some more examples. Actually, I just graphed this one, didn't I? So one of them is a nice parabola like this. The x minus 3 takes the parabola and shifts it just over to the right. I always have to use my hands and like figure which one is left and right. So which way does each graph translate then? If it's an x minus 6, is it going left or right? Which way do negatives go? It goes to the right, yeah. Right by 6. So it's going that way. That may seem backwards, but hopefully my logic makes sense. Is before you get to use your function machine, you're getting robbed by $6. So therefore, bring $6 extra so that you have the money you need. Bringing $6 extra means positive 6 more. Seems backwards. This one then is going to be left by 3, and it's going backwards that way. This slide right here, I just wanted to talk through, well, what is happening to make the black graph get to the dotted graph. So in the first example here, what does the dotted graph look like compared to the black graph? Which way has it gone? It's gone to the right. Does that make sense? So here's how I might notate this. I might say that this graph right here is the f of x graph. And then I might say that the dotted line graph, I'm just going to draw an arrow there. I might then say that the dotted line graph, you could write it like this, is the g of x graph. And it is equal to f of x minus 3. Because it's over to the right 3 units from the f graph. The f graph and the g graph are the exact same, except one of them is 3 units that way. We do the same thing here. Let's say I'll do a new color here. Let's say that this graph right here we call f of x. Then it means that this graph right here is f of x minus 2. Why? Well, it's 2 further down. What's up? Oh, there you go. So these bottom ones, you can actually do both. Let's say that this graph right here is f of x. And then we want to do, well, what is the dotted line graph? It looks like it's gone up 1 and backwards 2. So it'll be f of x plus 2 plus 1. The plus 1 afterwards moves the graph up. And the plus 2 on the inside of the brackets actually moved it backwards for us. Does that make sense? Okay, one last one. Let's say that this graph here is f of x, and I want to name the dotted line as a g of x. How does g of x compare to f of x? Well, it looks like it goes over 1 and down 1. So how would I write that then? And we'll take a stab at it. It actually, in order to go that way, it needs to be a minus 1. So like, it'll be f of x minus 1. That will make the graph go to our rights. And then to go down will be an extra minus 1. Is that what you said? You get a plus 1 in there somewhere. Yeah. Okay. Does that make sense? So this makes it move that way, and this makes it move that way. Again, the whole point of this is we wanted to try to find a way to take a graph from one location and say, well, I don't want it in this location, I want it somewhere else. And so this is how you move a graph congruently. It's the exact same graph, it's just been slid over or down. So if it's inside a function, it moves it left or right. And if it's outside a function, it moves it up and down. it does not matter what the function is then. Okay. So far, we've learned about linears, cubics, quadratics, okay? But later on in the course, we're going to learn about how to do sines and logs and exponents. This applies regardless of whatever the function is. Okay. So if I were to tell you that there's a function, but inside the brackets, inside the function you have to add 2, what does this mean you're going to do to a graph? Which way? Left, yeah. This is going to go left by 2. Good, up by 9. I don't care what the graph looks like. Whatever graph it is, if you apply this transformation, that's what it'll do. So what I want to do now is show you, well, how would I write this transformation into a whole bunch of different functions? Some of which we've done, some of which we haven't done. So let me try some with you here. Let's say the function was x squared. Before I square the function, I need to add 2. So it would look like this. X plus 2, then square it. That would cause the graph to go backwards by 2. When I'm done, then I'd add 9. This would cause an x squared graph to go backwards and up. Does that make sense?
Yeah.
So same thing with an x cubed graph. If I want to make it go backwards and up, before I cube the thing, add the 2. And then add 9. This is like, I'm kind of counting on getting $2 extra before I start. So I actually need $2 less. So that's why my x's are a little bit less than they normally are. And then after I'm done, everybody gets $9 free. So that's why the whole graph goes up by 9. My vending machine analogy is not perfect. It would be awesome. What about if it was a square root then? Well, take your x and add 2 before you square root it. And then after you're done square rooting it, add 9. This is kind of like the f g x all in brackets. Remember like the notation f of g of x? To some degree, I have too many brackets there. What we're doing is we're shoving this little function inside the function. Does that make sense? Like we're putting something inside of something else. That's why I wanted to show you that notation first. Anybody want to take a stab at this one here? And then make sure you're done with the fraction, then add 9. Good. I'm running out of a little bit of room here. This would be the absolute value of x plus 2, then add 9. Well, we can do this with crazier functions you haven't ever even seen before. The same principles applies. This will be the log of x plus 2. And then when you're done, add 9. This will be 2 to the power of x plus 2. And then when you're done, add 9. Even though you don't know what these graphs look like, you don't need to. We will eventually talk about those graphs. Like that's later on in the course. But the same skills will apply then. What about if there's more than one x? For both x's. Yeah. So make it x plus 2, then square. Add 3, x plus 2, plus 6. And then when you're done all of that, add 9. The 6 and the 9, by the way, you could add them together.
So you only add like the last number left with the one time, like you wouldn't put it in?
No. So like this is supposed to be your function kind of right here. Once we're done with all of that, then add 9. But that plus 2 only goes inside where x was. This one would be sine of x plus 2 plus 9. And then one more. I'm just kind of going crazy on this last one. Everywhere you have an x, replace it with x plus 2. So this would be 4 x plus 2 to the 3 plus sine of 4 x plus 2 minus 4 to the power of 4 with like an x plus 2 minus an absolute value of x plus 2. And then when you're done with all of that, at the very, very end, save a little bit of room for a plus 9. All of these graphs, whatever they look like, I mean, like I said, we don't know what these graphs look like. But I mean, let's say the graph looked like this. What would have happened, and this is something neat that I can do on my smartboard. I can select, hang on a sec. so that I can do this properly. Here's a grid. Here is a function that I've drawn. That's not even a function, but it'll work. I should be able to select this, copy, paste, and then what I could do here is say, well, here's where it should have been. All of these graphs should be moved up 9 and over 2, and that's where the graph would be. Does that make sense? Okay, I want to be done really soon here. We've actually talked about this a little bit before last year. We talked about something called vertex form. You guys recall this? Here's standard form. Vertex form was where you had like the A out front, you had all this stuff factored, and if you guys recall at all, H and K was where your vertex was. We actually learned a little bit about this before, actually. We didn't know it as translations yet. But I got 3 last examples, then we'll call it a day. So now let's apply this knowledge to 3 different types of questions you might get asked on like a test or assignment. So here's the first one. Let's say that I give you some points. Could you tell me where the new points would be after we move them around? So, -2 and 5 would be up here. 0 and 0 would be right here. 2 and 4 would be right here. And 3 and 2 would be right here. What I'd like to do now is take all of those points and move them. So I'm going to cheat because I can. I'm going to select them and copy them. Copy, paste. What does this notation mean to do? What does the -2 mean? Okay, so there. Now they're all to the right by 2. I wish I could change the color because that's kind of confusing. But maybe rather than doing it like that, I'll do it with a different color then. So this one would have gone over 2 and up 1. This one would have gone over 2 and up 1. This one would have gone over 2 and up 1. And this one would have gone over 2 and up 1. The question then may ask you, well, what are the coordinates of those points? And you'd say, well, this point is now at 0 and 5. This point is now at 2 and 1. This point is now at, is that 5 and 4? I think this one is now at 4 and 5. Does that make sense? So a question might then ask you, well, where have all of these 4 points ended up when you're done? And the purple answers would be where they've now been moved to. Does that make sense? Okay, so that's one place that maybe you could apply this new skill. Similarly, maybe I could give you a picture of a graph and say, draw me where these new graphs would be. Now, just so you guys know, on the diploma, that you can't actually be asked to draw a graph, but I have seen it asked before where they gave you the original graph, and they told you that it was supposed to get moved, like, say, over and down, and they gave you 4 pictures, and they said, which is the right picture. That makes sense? Because you can't actually ask to be drawn this on a multiple choice test, but I will ask you to draw them at first. So, what does this -1 mean? So it would be right there. Slide it that way. This guy right here, what does the +2 mean?
Over and left.
Pull it backwards to the left, but don't draw this in too thick just yet, because this -3 over 2 means you've got to actually pull it down. Like that. I can just pick it up and literally move it. But you'd have to move it over and then down 1.5 points. Does that make sense? What about this one here? I've kind of messed things up a little bit here. What does the +4 mean? So we're going to the left by 4. What does this -3 mean? Good. It means go up, because see how the 3's on the wrong side of the equation? They were supposed to go up. So let's see whether I can do this. It's a lot easier for me because I'll just trace the thing and I'll pick it up. So we need to go over 4, so that'd be 1, 2, 3, 4, and then up 3, so that's 1, 2, 3. So it should be basically up there. If you have to, just count it out point by point. So like I'd take this point and go over 1, 2, 3, 4, and then go up 1, 2, 3. And maybe I'd take this point right here and go over 1, 2, 3, 4, go up 1, 2, 3. Does that make sense? Like try it point by point. You guys get the point?
Yeah.
Okay, cool. I'll skip the last one. Last example. This is probably the most likely kind of question where you have to apply something. So a lot of reading first. This is my last one, right?
Yeah.
Okay, good. Perfectly on time. A quadratic function has roots of -2 and 3 and goes to the point 1, -12. I just want to stop there. If I were to graph the original information, what would it look like? A root at -2 and a root over here at 3. It's quadratic, so I know that it either does upside downiness or right side uppiness. I like making up words. I can actually figure this out by knowing where that other point is. That 1 minus 12 means that there's a point way down here at 1 minus 12. Is this going to be a frowny face or a smiley face? Yeah, so based on the information I have, I actually know the leading coefficient should be positive. It's the only way it's going to work, right? Fine. Everything I just did there was based on just the first sentence. It then says the transformation undergoes x plus 4 inside the brackets. So that means everything moved to the left 4. So everything moved that way by 4. My new question is, once I've done that, so I'm just going to sketch this real quick. I'm going to do it in red so that I can actually pull it over. Now it says, what's the new y-intercept?
Oh, I thought it was next to the left, not to the right.
Ooh, good catch. Thank you. I have taught you well. Apparently. That way by 4. Thank you. Good catch. So it actually should have gone that way by 4. Does that make sense? This is what we're looking for. What's the y-intercept? This would be a great numerical response question because they could just ask you what is the number, and the number is, I don't know, like -7 or something. Does that make sense? Any thoughts? How do we find this y-intercept? I mean, I know about where it is, but how do I find exactly what its value is? You know what? It would really help if I actually had an equation. Because I don't actually have any equations yet, do I? Could we write the equation for the black function?
Hey, Chris, could I interrupt your class for like, not even a minute?
Sure, go ahead.
Hey guys! I'm Constable Victoria March. I'm the school liaison officer for FP Walsh. If you guys can't remember my last name, Constable Victoria or oh, the cops are here, everyone's around, it's fine. I'll be in the school probably on a weekly basis. Meet in the hall, say hi. If there are any problems, feel free to talk to me. And of course, my role, if you guys get in trouble, you'll have to talk. Any questions?
Thank you.
Yes.
My card was down.
It's okay. Okay, I've got 1 minute left. I'm going to take 1 more minute because she interrupted me. So I promised to be done here. We can write an equation for the black one, though. Okay, we've done this before. You could say y equals, we don't know the a value, but I do know the x-intercepts were at -2, so I'm going +2. And they were at +3, so I'm going -3. Does that make sense? How do I find that a value, though? We use the other point of the -12 and the 1. -12 will equal, that's going to be, that should be a 1 right there. That's 3, that's -2, so I think it's -6a. So a is 2. So far so good. Okay, so I now know the black equation was actually supposed to be 2x plus 2 x minus 3. Come on in. I'll take another minute here. Hey, come on in. Anybody for breakfast? Go ahead. I'm almost done, I promise. Like, we are at the last step, so. Sean, can you get me one yogurt? Just any flavor? That'll work. Thanks. Just throw it on the desk somewhere. Make it work. Alright, we good so far? I promise. We're like 2 steps away from being done here. This is now the equation of the black graph. How do the black graph and the red graph compare to each other? Well, one of them is 4 units that way, right? And this notation right here basically meant take all of your x's and add 4 to them. So to get from the black graph to the red graph, I'm just going to use a new color here. The new red graph means wherever I used to have an x, add 4. So it'll be x plus 2. Well, now it'll be x plus 4 plus 2. And rather than it being x minus 3, it'll be x plus 4 minus 3. Does that make sense? I basically, wherever I used to have an x, I put an x plus 4. Now we have the red graph equation. Well, if I have the red graph equation, I should be able to find an intercept from it. So let me just simplify it, because this is not much further. This is now x plus 6. This is now x plus 1. Actually, earlier today, Driano, I was talking with you about the idea of trying to find the y-intercept. If we actually expanded this out, we should be able to find that last number, the constant term. And I don't actually want to expand this whole thing. I just want to focus on the coefficients, though. At some point, this last number that's going to go at the end here is going to be 1 times 6 times 2. So that's 12. I don't actually have to go through the process of expanding it all, but I could have. The other possibility is type this in your graphing calculator and look for the y-intercept then. That makes sense. So in terms of steps for this one, sorry I went a little over what I promised. We used the first information to get the black graph. Once we had the equation for the black graph, we knew that this notation right here means move it 4 that way. Well, to make the graph move 4 that way, all we have to do is make x become x plus 4 everywhere. And then once we had a new equation, we just found the y-intercept. Apparently, I didn't draw my graph all that well, so maybe it was supposed to be a little bit further over. Maybe it was supposed to be a little bit more like that, I guess, so that the intercept was way up there. I probably didn't draw it all that well. So, summary, then go take a break. If you want a graph to go up, add a number well afterwards the function is over. If you want it to go down, subtract a number way the heck on the outside of the function. Those ones are usually the easiest ones. If you want it to go right or left, it's backwards. So negatives inside the function will cause it to go right, and positives will make it go left. Use that skill then to solve problems. Sound good? Cool. Okay, rest of the class is yours to work on the assignment. Sorry I was a little over.